Hello everyone, my name is Govinda Tapadia. I am currently pursuing BTech in Computer Science from Acropolis Institute of Technology and Research, and today I will be explaining you the given topic paging in operating systems. So let's move. Introduction to paging in operating system. Paging is a fundamental memory management technique used in modern operating systems. It allows the operating system to efficiently manage the allocation and utilization of memory by dividing it into smaller, fixed size units called pages. This presentation will explore the core concepts, benefits, and challenges of paging in operating system. Let's move to the definition of paging. Paging is a memory management technique that is used in computer operating systems. It involves computer's physical memory into fixed number of size of blocks called pages. These pages are then mapped to virtual memory, which is a way of providing memory than the computer's physical memory can support. The purpose of paging is to enable more efficient use of available memory by allowing programs to be broken up into smaller, manageable chunks. This helps to prevent memory fragmentation and allows the operating system to swap pages in and out of memory as needed, providing a seamless experience for the user. Purpose of paging. The primary purpose of paging is to in operating system is to enable efficient memory management. By dividing the physical memory into smaller blocks, fixed size called pages, the operating system can better utilize memory resources and provide more flexible virtual memory capabilities. This allows programs to access a larger amount of memory than what is physically available on the machine, providing the illusion of contiguous address space. Paging also enables memory protection as each page can be marked with access permissions, preventing unauthorized access to certain areas of memory. Additionally, paging facilitates memory sharing between processes and allowing multiple programs to utilize the same physical pages again, improving overall system efficiency. Let's move to the page table and page table entries. In paged memory system, the page table is a critical data structure that maps virtual memory addresses to physical memory addresses. Each page table entry in the table corresponds to a fixed block of memory called page. The page table entry contains information such as physical frame number, as I already said, access permission, and flag bits indicating whether the page is present in physical memory or has been saved out of the disk. For this, we use valid bit for 1 and invalid bit 0. The operating system uses the page table to translate virtual addresses requested by a process into the corresponding physical address in memory. This transition is done by the memory management unit, which consults the page table to find the physical frame number with the given virtual page. The page table entry also helps the OS to manage the paging process, including the handling page faults and implementing page replacement policies. Let's move to page replacement algorithm. We have many types of page replacement algorithms which are very crucial for uh, paging process and allocating the processes. Page replacement algorithms are crucial in the management of virtual operating system. These algorithms determine which pages in memory should be replaced when new pages need to be brought in, ensuring efficient utilization of available memory. Some common page replacement algorithms include first in, first out, least recently used, optimal page replacement. First in, first out is a simple algorithm that replaces the old page in the memory while least recently used replaces the page that has been unused for the longest time. On the other hand, optimal page replacement is an ideal algorithm that replaces the page that will not be used for the longest time in the future, though it is not practical to implement in real world systems. Each algorithm has its own advantages and trade offs, and the choice depends on the specific requirements of the system. Let's move to demand paging. Demand paging is a memory management technique or we can say demand paging is needed when the system requires pages, and it is a it is it is the best feasible way or optimal solution for paging or efficiency. Demand paging is a memory management technique used in operating system where pages are loaded into main memory when they are needed by a running process. As I already said, this is in contrast static paging where all pages are loaded into memory at the start of the program execution. Demand paging helps to optimize memory usage by only bringing in necessary pages, reducing the overall memory footprint. With demand paging, when process try to access a page that is not currently in memory, a page fault occurs. The operating system then loads the required page from the secondary storage, such as hard disk or SSD, into an available frame in main memory. This can incur a significant delay known as page fault handling time, which can impact the overall performance of the system. Effective demand paging strategies, such as use of page replacement algorithms, aim to minimize the number of page faults and optimize the use of available memory. Be careful managing the replacement pages in memory. The operating system can improve the overall efficiency and responsiveness of the system. Let's move to the page fault handling. When a running process attempts to access a page that is not currently in memory, it triggers a page fault. The operating system must then handle this fault to ensure the process can continue executing. This involves locating the needed page in secondary storage such as hard disk and bringing it into the main memory. The process is then resumed from the point where the page fault occurred. The operating system uses a page fault handler and manage this process. The handler first checks if the page fault was due to valid memory access that simply requires a page to be loaded. If so, it retrieves the page from secondary storage and maps it into the process address space. If the page fault was due to an illegal access, the handler will terminate the offending process. Let's move to the thrashing and its causes. Thrashing is the phenomenon that occurs in virtual memory systems when a computer spends more time swapping pages in and out of memory than actual executing instructions. This happens when the system working set, the set of pages needed to perform a task, is larger than available physical memory. As a result, the system is constantly paging, leading to a severe performance degradation. The primary causes of thrashing are high page voltage, a lack of memory, and poor page replacement algorithm. When the working set exceeds the available memory, the system is forced to constantly swap pages in and out, leading to a high number of page faults and significant slowdown in overall performance. Now, the best part is benefits of paging, and the best utilization for this is efficient memory utilization. Paging allows for more efficient use of available memory by dividing the physical memory into smaller manageable pages. This enables the operating system to load out only the necessary pages into the memory, reducing the overall memory footprint. Now, second benefit, simplified memory management. Paging simplifies memory management by abstracting the physical memory layout. The operating system can easily map virtual addresses to physical addresses, making it easier to allocate and deallocate memory as needed. Better process isolation. Paging provides a level of isolation between processes such as each process has its own virtual address space. This helps this helps prevent one process from inadvertently accessing or modifying in the memory of another process, improving overall system security and stability. Let's move to the limitation and challenging of paging. Memory fragmentation. Paging can lead to memory fragmentation where free memory is divided into many small unusual blocks. This can reduce the overall efficiency of memory usage and cause performance issues, especially for applications that require large contiguous blocks of memory. Second challenge, overhead and complexity. Implementing and managing a paging system adds significant overhead and complexity to the operating system, as we need page tables, virtual address spaces, and page replacement algorithm, which makes the operating system more complex and resource intensive. Performance challenges. Paging introduces performance challenges through which latency is increased, reduced throughput, and extra steps to convert virtual addresses to the physical addresses, and page fault handling increases. And this can be especially problematic for real time constraints and with high memory demands. Thank you.